just in case. Okay, I'll be right back after I grab a calculator. So now I think we're ready. All right, so number one here through what? 5 through 5 is all acid base, which is it's your exam. I wouldn't say it's like super heavy acid base, but it is like more than a little. So hopefully lab went well. Um, and hopefully this is a like review. The lab was a good review, and this is, a good review. So number one, what is the hydroxide ion concentration of a solution whose H3O plus is 1.0 times 10 to the negative 10? So hydroxide ion, that is OH minus. So we're talking about base here, the concentration of base. And so if we're wanting to find OH and we have H plus, we're going to use the KW formula, where KW equals 1.0 times 10 to the negative 14th, which is equal to OH concentration times H plus concentration, and we can enter that here. So we'd have OH minus equals, sorry, one more person joining, equals 1.0 times 10 to the negative 14th divided by 1.0 times 10 to the negative 10th, which should give us 1.0 times 10 to the negative 4th. Wonder if I can change this pen. All right. Any questions there? All right, we'll keep moving then. So number,
Yeah, I just got into
okay. All right.
Thank you.
All right. So if the pH of a urine sample is 3.34, what is the OH of the sample? So here's where we're going to need like the acid base square. So we have pH, we know how to get to the concentration of H plus or POH, and we know how to get to the concentration of from POH or H plus to OH minus, but we do not know directly how to get there. So it's going to be a two-way stepper. So I prefer to go this direction. So pH plus POH equals 14. So to find POH, I can do 14 minus 3.34, which equals, that's where we got the calculator, 10.6. All right, so that's my POH. So now I'm here and I can go to OH minus. So that formula you would be given on like your reference sheet. But to go from POH to H plus or OH minus, sorry, it's OH equals 10 to the negative POH. So I would take this 10.6 and put it as an exponent here. So when I do that, when I put into my calculator 10 to the negative 10.6, sorry, Ah, dang it. This stupid calculator. I have to use my phone. All right, so 10 to the 10.6 negative, and I get 2.51 times 10 to the negative 1, 2. Oh, here we go. Negative 11th. All right, so that's our OH concentration. All right, so pH would have been a one-stepper if we wanted to go to H plus, but since it was asking about OH concentration, it was a two-stepper. So here was our first step, getting to POH, and then using that to get second step to get to OH. All right, no questions, we'll keep moving forward.
No, I do got a question.
All right,
Huh?
go ahead.
Oh, okay. For the exam, like, how do the questions look? Do they look similar to the owls, or do they look similar to the the knowledge check? Like, what do they look like?
They look more like this, but they're multiple choice.
Oh, okay. So we'll have some type of scrap paper or something like that to work it out, and then.
Yep.
Or, okay.
Yep, and I'll print you off a reference.
Oh, what you was saying? My bad. I'm sorry.
I'll print you off a reference sheet too.
And then also, thank you. And then also, how many questions is there?
50, I believe.
Oh, geez. Okay, thank you.
Anybody else? All right. So number 3, we're still talking about acid base. So we have here, so like I said, I wrote this wording like this is like wording you would see on the exam. Like I literally just changed the numbers. So one of your questions says a client with respiratory alkalosis has an H3 plus concentration of, and then I changed the number, 5.76 times 10 to the negative 4 molar in their blood plasma. So what is the pH? All right, so we're given H plus. So we're here where I had it circled. And now we just need to go to pH. Again, you would be given this formula, pretend you have a reference sheet in front of you, but pH equals the negative log of H plus. So this one is just a matter of putting this into the formula and then plugging it into our calculator. That's a negative 4. So when I do that, let's see, negative log. I get pH equals 3.24, which I briefly mentioned this in lecture, but a good way to check yourself is that your exponent and your pH are similar. So like 4, I would be expecting a pH that's in the 3s or in the 4s, maybe in the low 5s. But if I got a pH and that it was like 10, that would be kind of a red flag that maybe I messed something up. And even in this problem, number 2 here, so the pH was 10 point, or the POH was 10.6. And then when I did it backwards, I got an exponent of negative 11, which again is kind of in that range, right? It's not like I had a POH of 10 and got back an exponent with a 3, right? You want those to kind of align. I'm not going to say they're going to perfectly align, but like it should be only a digit or 2 off. All right, any questions? So I am recording, but I will erase unless I get an objection. All right. So now we'll scroll down. Okay, so what is the formula of the conjugate base for HCl? So HCl, let's go back to this red. HCl is an acid, and so a conjugate, whatever you're doing the opposite of it. So if it was a base, you'd be making an acid, and if it was an acid, you're going to be making a base. So an acid, quote unquote, has the ball or has the hydrogen and wants to donate it. So a base would lose that hydrogen. And that hydrogen is equal to H plus, essentially. So if HCl is neutral and I got rid of something with a plus charge, now I have something with a negative charge. All right, so this would be my final answer.
Okay, read it one more time.
All right, so number 5, determine the Bronsted base on the reactant side of the following equation. All right, for the sake of practice, we can identify everything, but like I said, this is a multiple choice question. I've just written it as a free response, so you would be picking, like, say this was listed as A, B, C, D kind of thing. But for the sake of review, we can label.
Right. Number that has an 8 in it with a value that is 10 times the value of the 8 in the number shown.
It appears that maybe one of you guys has your mics on that you don't want to have your mic on. All right. So let's match them up with their partners. So it looks like H2SO4 looks pretty similar to, let's erase this line, HSO4 minus, and H2O seems to resemble, oops, the line went away. Seems to resemble H3O. So here it lost a hydrogen. So it donated a hydrogen to solution, which is an acid, making this the conjugate base. And then here, the H2O picked up a hydrogen. So it accepted a hydrogen, making it the base. And this guy, the conjugate acid. And so A, B, C, or D here, you would choose the answer choice that has water, H2O. All right.
So I have a question.
Yeah, absolutely.
With that problem, you basically just remember, acid loses a hydrogen, base gains one, and
Yeah.
yeah.
Yeah, no, perfect.
Okay. Okay, thank you.
I got a question though. What about when the arrows be like half arrows?
Oh, like this?
That's how it was on the I think it might have either been on the owls or on the knowledge check. It asked about the Bronsted base, but it was like it took me a minute to get it, but it was like the half arrows. Yes, like that. Yeah. Mm-hmm. So
Yeah.
how do you determine like then the
So even with these arrows, the reactant side is still the left side. This is still reactant. And the right side is still the product side. It's just these arrows are saying that the reaction can go forward and backwards, but as it's written, the reactant is still the left and the product is still the right. So like
What you say?
this question asks for the base on the reactant side. So you're looking for the base that's on the left side.
Okay, thank
So
you.
8 times 10 is
Again, it seems like one of you has your mic on.
It's not telling you to make the same number, it's telling you to make a new number where the place value of the 8 is now, if that's the ones place, but it's now going to be in the tens place.
Sharina, your mic is on.
Sorry.
Thank you. I was trying to go mute it for her, but that was a hot mess. Okay, so number 6. So we're out of acid base. We're into our concentration, which this was module 3. So calculate the percent weight volume in the units of grams per mil of a solution prepared by dissolving 2.13 grams of sodium chloride in enough water to give 0.3 liters of solution. So percent weight volume. What to remember? It's part over total times 100. All right, so for here, we'd want to do, and this one is also telling us to be specific with grams per mil. So if we're dissolving 2.3 grams, that's our part in 0.34 liters of water, which we need to change to milliliters because it's telling us that it needs to be in milliliters here. So, if we do King Henry died by drinking chocolate milk, right now we're in our base unit when we're in liters, and to get to milliliters, we're gonna have to bunny hop 1, 2, 3 decimals to the right. So 1, 2, 3. This is kind of a mess, so I'm gonna erase it. Oh, not the whole screen. I didn't mean to do that. All right, so 340 milliliters. All right, so that's our part divided by our total. And we would do times 100. And when we plug this in, 2.13 divided by 340 times 100. Oh. All right, even though I times it by 100, I'm still getting something that's less than 1%. That's probably just because I made up the numbers, but I'm getting 0.63 when I round percent. I would guess that your guys's, that's probably just weird, less than 1% because I made up the numbers. Any questions? All right, I'm going to erase. All right, we'll keep chugging along here for 7, 8, 9. All right, so 7. This is an example of a molarity big M question, which again came from our last module 3 lecture. So normal saline solution used for IV drips contains 1.1 grams of sodium per 0.7 liters of solution. What is the molarity? So big M. So what to remember is that big M is not what I'm writing. 1 second, sorry. There we go. Big M is moles over liters. So in order to solve for this, we need to have moles and liters, and right now we don't have that. We have grams and liters. Oh, I'm sorry. So we do have liters. So we need to go from grams to moles. So grams to moles of NaCl, we would need the molar mass. So the molar mass of NaCl is 58.44 grams. So we would put our given unit on top. Then we want to cancel with the unit on bottom and then our new unit in based off of the conversion factor on top. And the number is always married to the gram. So it's going to go on bottom with the gram, and that would leave 1 mole on top. And then we calculate 1.12 divided by 58.44 equals 0.019. We'll round to 2 moles. All right, so now I have moles and I was given liters, and now I can finally go plug these in to my big moles over liters. So I'm going to change to blue here because we're getting kind of messy.
Professor Daniels, I have a quick question.
Yeah.
When you're canceling out, the NaCl stays, right?
Yes. This is
Okay.
still NaCl. Yep.
Okay.
All right. So now we have all of our information to do moles over liters to get big M. So we found that our moles is 0.0192, and our liters was already given to us in liters in the problem, 0.70. And so when I plug into my calculator, 0.0192 divided by 0.7, our big M would equal 0.027. All right, number 8, if there are no questions. All right, number 8 is the partial pressure law. So this was what we learned right at the end of module 2, I believe. So a gas mixture of neon and argon has a total pressure of 1.7 atmospheres. The partial pressure for neon is 0.89 atmospheres, and they want us to calculate the pressure partial for argon. And so the partial pressure law basically says that the total pressure is the sum of its parts. So the sum of part 1 plus part 2. And if there's 3 parts, then 3, plus 3. So if we have the total 1.7 atmospheres, and we know that one of the parts is 0.89 atmospheres, we can solve for the other part by calling it x and subtracting each side by, in this case, 0.89 to get x by itself. So 1.17 divided by, multiple. All right, so 0.81 atmospheres. So that one's pretty straightforward. So the one that you're looking for, it's called partial pressure. So when you see something on the test that talks about partial pressure, that's that problem here. Any questions? All right,
I have a question.
go ahead.
So on this one, on 8, why do we subtract the 0.89 instead of the instead of the 1.70?
1.70, you're trying to get x by itself.
Okay, got it. Okay.
Yeah, sorry, it's kind of a hot mess right over here. X is here. All right, I'm going to erase, even though we have number 9 still on the screen. I just feel like it's really messy and stressing me out. And again, this is all recorded, so. All right, let's move number 9 up here. All right, so number 9 is the dilution equation. And again, you might be looking at that and being like, Kayla, how do you know it's the dilution equation? All right, and again, this wording is verbatim from your test, and I just took different numbers. So how did I know it was the dilution equation? A couple reasons. One is it uses the word dilute in it. And again, this language is verbatim for your test. So when you see something that says dilute, you know that you're looking for the dilution equation. Second, I have 3 numbers, 2 which have the same unit, implying that I'm looking for a 4th number, which is what the dilution equation solves for. So the dilution equation is C1V1 equals C2V2. And we want to make sure that we're in the same units on each side. All right, which looks like it's not going to be a problem. So how I like to solve these is set up all my variables that are given to me in my equation. So in a laboratory, a student dilutes 34.5 milliliters. So that must be my volume 1 of 2.75. That's my concentration 1, big M, to a total volume of 300 mils. So they're telling me the total volume at the end here, which is great. And then it says, what is the concentration of the diluted solution? So that's my X, or my variable. All right, so now it's just a matter of plugging these numbers into the equation. So we have 2.75 here times 35.4 here equals X times 300. All right, and then so to get X all by itself, we would want to divide by 300 on both sides. And in this case, X is going to be 2.75 times 35.4 divided by 300.
It's supposed to be 34.5.
Oh, did I? Oh, yeah, I mixed the numbers. Thank you. Okay, so okay, let's try that again. All right, so this is what I got. So the new concentration would be 0.316 molar, which again, it would make sense if I wanted to double check myself. I know I'm diluting the original concentration, so I'd want a number that's smaller than that. All right, so this is smaller, so that makes sense. Any questions about the dilution equation? All right, we're going to move down to number 10 now. All right, so 10 is an example of our other gas law, which is the ideal gas law. And so again, how did I identify that? So ideal gas law is PV equals nRT, where you have all these different variables with different units. And so here I see mole, but then I also see liters, and I see a temperature, and I'm being asked what's the pressure. So for me, that cues ideal gas law. All right. So with ideal gas law, you have all these variables, right? So you'd be given this on the test. All right. So P stands for pressure, and you need to be in atmospheres. All right. And so in order for this formula to work, you have to be in that specific unit. V is volume, and you have to be in liters. What comes next? N is moles. R is a constant, and you'd be given this constant on your formula sheet, but it's 0.0821. And then the tricky one here is T is temperature, but in Kelvin. And so how this problem is given to you on your exam is that you're given moles and moles, right? You don't have to do any calculations there. You're given liters and liters, but you're given the temperature in Kelvin, or I'm sorry, in Celsius, and you have to go to Kelvin. So to get to Kelvin, it's Celsius plus 273, right? And that would also be on your formula sheet. So in this case, it would be 298 Kelvin. All right. So now that I have all my variables in the correct unit, I'm going to go ahead and list them off to the side. I'm going to erase this other stuff I have going on because, again, it's just kind of messy. All right. So my P is what I'm solving for. So we'll call this X. V is nope, not 6.75 liters. my N, 3.4 moles. My R is already going to give to me. That's going to be in a formula sheet. And my T is 298 Kelvin. So now I can go ahead and plug that into this equation here that I wrote beforehand. All right. So P is my X, V is 6.75 equals N is my moles. So 3.45 times R, you get this from the formula sheet, times 298, that's my temperature in Kelvin. All right. And so then to get X by itself, divide each side by 6.75 and plug and chug away in your calculator. So 3.45 times 0.0821 times 298 divided by 6.75. And I get the pressure equals 12.5 atmospheres. Any questions? All right.
And so when you just plug it in how the equation is written, right?
Yeah, I plugged it in and then manipulated the equation, but it's totally okay if you wanted to manipulate the variables beforehand. You should get
Okay. Okay.
All right. So go ahead and delete this because it's really messy. I don't know why it's bothering me so much today, but it is. Okay, so number 11. This is just changing units of pressure. So if you remember, there was a slide where we talked about the units of pressure right in module 2, right before the gas laws. And I had this like equation in blue where it was like 1 atmosphere equals this, blah, blah, blah. So you would get that from the reference sheet. I'll tell you right now that 1 atmosphere equals 760 millimeters mercury, which is the part we're going to have to use today for this problem. So a client has a systolic blood pressure of 345 millimeters mercury, and we want to express this pressure in the unit of ATM. So we're going to start with our given, 345 millimeters mercury. We want to, this is our conversion, so we want to get out of millimeters mercury. So we're going to put that on bottom and into atmosphere. So we're going to put that on top, where 1 atmosphere equals 760 millimeters mercury. And so those will cancel and leave us with our desired unit on top. So it's just a matter of taking 345 divided by 760 for the answer to be 0.45 atmospheres. Any questions here? All right. So number 12, now we go back to week 2 with our stoichiometry. And how do I know this is stoichiometry? Couple reasons. One, I'm given an equation. All right. That cues me that this is a stoichiometry problem. 2, I'm asked how many grams of iron, and then my given is in a whole different unit. All right. So changing substances also cues me into the fact that it's a stoichiometry problem. All right. So I'm going to start with my given, 4 moles of Cl2. All right. And so to switch substances, I need to be in moles. All right. So if I was given grams, I would need to go to moles next. But since I'm given moles, I can go ahead and switch substances. All right. And then I'm going to use the coefficients in the balanced equation to do that. All right. So this balanced equation here, let's erase this one. All right, so I'm going to want moles of Cl2 on bottom since I want these to cancel out. And then I'm going to go into moles of my desired unit on top, moles of iron. So here it looks like we have 2 moles of iron for every 3 moles of Cl2 chlorine. All right, so now I'm in moles up top. I'm in my desired unit. I'm sorry, I'm in my desired substance, but not my desired unit. So now I need to go from moles to grams. All right. And I can do that using the molar mass of iron. And so I'm going to have to quickly get that. I'm going to Google it, but you can get it from the periodic table if you have one in front of you. Molar mass of iron. All right, so it's 55.845 grams per mole. All right, so next I'm going to put moles on bottom so that way they cancel and grams on top, which is great because grams is my desired unit. And this is all of Fe or iron. All right, so the number is married to the gram. And so since the gram is on top, that's where the number is going to go, leaving 1 mole on bottom. All right, so now I'm out of moles of Fe and I'm into grams of Fe, which is what I want for my final problem or final answer, which is great. So now it's just a matter of plugging this into my calculator. So 4 times 2 times 55.845 divided by 3, I get 148.9 grams of iron. Questions? All right. Let's go ahead and delete this and move on to 13. All right, so we're looking at another stoichiometry. So how do I know? I'm given an equation, first of all. Second, I'm asked how many moles of iron chloride, and my given is in chlorine, all right, or chloride. So it looks like we're going from moles to moles, which is great. That's going to be just a one-stepper, all right? Because moles is how I change substances. So if I am given moles and I want to end in moles, it's just a matter of changing the substances with the mole to mole ratio. All right, so I'm going to start with my given, 0.35 moles. All right, so moles of Cl2 on bottom because I want them to cancel. And then it looks like moles of iron chloride, FeCl3 on top, because that's my desired unit. So there is 3 moles of chloride for every 2 moles of iron chloride. And so 0.35 times 2 divided by 3 is 0.23 moles of iron chloride. These canceled. Any questions there? All right, we're chugging right along. All right, so 14 is balancing an equation. So how I balance my equations, I make sure I put a line down where the arrow is, I list all the atoms on one side and I list them in the exact same order on the other side. And then I do an initial count with tallies. So I have 3 carbon, sorry. 8 H's, 2 O's. On this side, I have 1 carbon, 2 hydrogens, and 3 oxygen. So there's a couple different ways we can start. I know that I'm gonna want an even number here because I'm gonna want an even number of oxygens eventually because I only have even numbers over here. But I think I'm gonna start with the carbons. So if I put a big 3 out front here, that will give me 3 carbons, but it will also change my oxygen count. So now 3 times 2 is 6, but we can't forget our other oxygen here for a total of 7. If I put a 4 in front of here to balance out the hydrogens, that is an even number, which I did want eventually for the O's. So 4 times 2 for the hydrogens is 8. So now these are balanced, but it does add 4 more O's to, well, technically it adds 3 more O's. But if we did a total count, we have 4 hydrogens, 4 oxygens by putting this 4 in front of here, plus 3 times 2 here is 6, bringing us a total count of 10. All right, so then I can just put a 5 in front of here to even out my oxygens. 5 times 2 is 10. There we go. Questions?
So you don't have to use even numbers?
Can you be more specific?
When you're balancing, you see how you have even for the 4?
Yeah.
So
So you don't have to use even numbers. I just knew that I was looking for an even number eventually for the coefficient on H2O because I can only have oxygen on this side in multiples of 2. So I eventually wanted to make this single oxygen. See, if I put an odd number there, I would continue to have an odd number of oxygen. And I wanted to eventually get it even because I knew I could only have even numbers of oxygen.
okay.
Any other questions? All right. Number 15. All right, a nursing student has a sample of methane gas containing 3.1 times 10 to the 19th molecules. How many moles are found in this sample? So when I see the word molecules or atoms or formula units, I'm thinking of Avogadro's number. All right, and the conversion there is that 1 mole equals 6.02 times 10 to the 23rd molecules. And that is a number you'd get on your formula sheet. You just got to know how to use it, right? All right. So we're going to start with my given 3.1 times 10 to the 19th molecules. All right. We're not changing substances or anything, so I really don't need to worry about carrying the CH4 with me, but you could. All right. So now I want molecules on bottom so that they will cancel. And I want moles on top. And I know that there's 6.0 times 10 to the 23 molecules. So I'm gonna put that on bottom down with my molecules, leaving 1 to go on top. All right. So that leaves me with moles, which is my desired unit, which is great. This is just a one-stepper. The trick here is to make sure you're typing it into your calculator correctly. So I'm going to make sure that I use open parenthesis here. I'm going to type 3.1 times 10 to the caret 19. I'm going to close my parentheses. I'm going to hit the division sign, open parentheses, 6.02 times 10 to the caret 23, close parentheses. All right, I'm going to do that now. 3.1. All right, so I got 5.15, just for the sake of rounding, times 10 to the negative 1, 5. All right, and this would be moles. I don't know why the pencil is doing like sometimes thin, sometimes thick. I'm sorry. Any questions? All right, 16. This is one of my favorites. Okay, so students, this one kind of stumps up students, but let me tell you what to look for here. So a student has 4 moles of C3H8. How many moles of hydrogen are in their sample? So we're going from moles to moles. And it appears like we're going from moles to moles of different compounds. But we're not given a balanced equation, all right? Which means although this appears like it's a stoichiometry, because we're not given a balanced equation, this is one where you use the internal numbers of the molecule, okay? So we're going to start with 4 moles of C3H8, right? And now we want to know for every 1 mole of C3H8, how many hydrogens are there? All right, we're going to use the internal numbers like I said. So for every 1 mole of C3H8, there are 8 H's. All right, so now we're out of moles of the entire molecule and into moles of just H's. So the final answer for this is 32 moles of hydrogen. So what this problem kind of reminds me of, it's kind of like saying, say you were like a really meticulous baker and you put 8 chocolate chips per cookie, all right? And so now you're saying, I have a recipe that makes 4 cookies. How many chocolate chips do I need total for my entire recipe? All right, so 4 cookies times 8 chocolate chips each, 32 chocolate chips, but in this case, moles. Questions? All right, we're going to keep moving on then. I couldn't remember how long this was, sorry. All right, number 17. A student needs 0.45 moles of NaCl. Calculate how many grams are needed. All right, so this should be simple, going from moles to grams, and vice versa is a skill we need for a lot of other problems. So this question is just there is a question like this on the exam where it just tests you on your fundamentals of going from moles to grams. All right. So we can go from grams to moles and moles to grams using the molar mass, right? And that's something we can find on the periodic table. So for this case, the molar mass of NaCl is 58.44 grams per mole. All right. So I'm going to start with my given 0.45 moles. And then I'm going to put moles on bottom because I want them to cancel, which leaves me with grams on top. This number is always married to the gram. So since the gram is on top, this number is going to be on top, leaving 1 mole for the bottom. All right. So now it's just a matter of multiplying 0.45 times 58.44. So 26 point, we're going to round 0.3 grams. Questions? All right. So this takes us all the way back to week 1, wherein we talked about protons, neutrons, and electrons. And we talked about this little formula that it's written in. Technically, this line shouldn't be here, but it was very hard for me to format it on Word without that line. But technically, a nuclear symbol doesn't have that line there. All right, so how a nuclear symbol works is you have the element, all right, and that would be the symbol there. You have here is the atomic number, which is also equal to the protons. Those are the same. This would be the number you'd find on the periodic table next to bromine. Here you have the mass number. And mass number is always protons plus neutrons. And then here you have the charge, which is equal to protons minus electrons. So with all this information, I can do a little bit of adding, subtracting, and find the number of protons, neutrons, and electrons. So the bottom left number is always going to be directly the number of protons. No math needed there. We're going to have to do a little bit of math to find the neutrons. So I know that the mass number is equal to P plus N neutrons. I know that the mass number in this case is 80 and the protons is 35, which leaves me with X here as N. So if I subtract 35 from both sides, I will get X by itself, which is the number of neutrons. So 80 minus 35 is 45. So I have 45 neutrons. All right. So 35 protons, 45 neutrons. Now I just need to solve for electrons. So that is going to be the charge equals protons minus electrons. So I know the charge is -1, and I know the protons are 35. So again, if we just set this up like an algebra problem, now this would be minus x. So to get x by itself, we're going to do this a couple ways. I am going to add x to both sides so that way I can make x positive. So now I have x minus 1 equals 35. Then if I plus 1 to each side to get positive x by itself, we have x equals 36. Which also, if you plug in 36 back up here to the original equation, 35 minus 36, a bigger negative number, right, is going to give you, I'm sorry, a bigger number that you're minusing is going to give you a negative number. So that makes sense. 35 minus 36 is -1. Questions here?
I got a question. I had went to tutoring.
Uh-huh.
And they told me the -1 mean you move one space back on the periodic table. So instead of me doing borium or whatever it is, I did krypton, is it? Is that not right?
That is totally not right. That's the first, yeah, that's not right.
Okay.
I'm sorry.
Nope, you're fine.
All right. Any other questions? All right, we'll move down to 19. All right, so why did that part not erase? That's so bizarre. Okay. We'll just ignore that. All right, so determine the molecular weight. So this is the same thing as molar mass. And so again, you're going to need this skill for a lot of different questions, but of course they'd like to ask a standalone question of this. So how do we calculate the molar mass? All right. So we add together all the individual molar masses to get it for the entire compound. So hydrogen, if we go to the periodic table, is 1.08 times 2, because there's 2 of them. So we'd have 2.061. And then we have oxygen, which depending on what periodic table you look at is, and we're going to just do 16 to make it nice and easy. So there's one of those. So I do 16 plus 2.016 for a total molar mass of water as 18.016 grams per mole. It's really messy. All right, any questions here? All right, we'll try to erase this. Again, that stupid box is staying. Why, I don't know. All right, 20. Again, this takes us back to the beginning of module 1, talking about temperature. So you would get these temperature formulas, but just as a reminder, all right, Kelvin equals Celsius plus 273. And it looks like we're also going to need the relationship between Kelvin and Fahrenheit. So Fahrenheit to Celsius is, let's see here. So Fahrenheit equals 9/5 times C plus 32. Yep. Okay. So we're given a temperature in Fahrenheit here, right? And we want to know what the temperature in Kelvin is. We don't have a relationship between Kelvin and Fahrenheit, but we do have a relationship between Fahrenheit and Celsius, and then Celsius and Kelvin. So first we're going to need to solve for Celsius. So I'm going to go ahead and rewrite this formula here. All right, and then I can plug in my 75.1. We do have to do a lot of algebra. So I'm going to subtract 32 from each side. 75.1 minus 32. So we have now 43.1 equals 9/5 C. And then to get C by itself, I'm going to multiply by the reciprocal, so times 5/9. And so I get C by itself equals 23.9. Right? So now I have C, and I can plug that into this formula up here to get Kelvin. So which happens to just be plus 273, which is great. and easy. So our final answer is 296.9 degrees Kelvin. Any questions? All right. Question. I think we have 3 more questions left. 21, 22. Oh, no, more than that. Okay. So 21. This also takes us back to lecture 1, using density as a conversion factor. So again, I'm sounding like a broken record, but this is how it's written on the exam. I might have changed the substance, this ethanol, but I don't think I did. I think I just changed the numbers. So it tells you that ethanol has a density of 1.23 grams per mil at 25 point C. That, when you see density, when you get to this density problem and you're given a temperature, just ignore the temperature. All right, they're just adding some extra stuff. All right, and then it says if 80.1 grams of ethanol is needed, what volume should be added? All right, so here's our given, and here's what we're trying to solve for. And we don't know the relationship off the top of our head from grams to mils. We need to be told what the density is, right? So we're going to use that density as our conversion factor. We're going to start with 80.1 grams, our given. And then we get to manipulate this density as needed, just like we would with molar mass, right? So this gram goes on bottom because I want my grams to cancel. Mils goes on top. All right. The 1.23 is married to the gram, so it goes on bottom with the grams, leaving 1 mil on top. And so now I'm out of grams and into mils, and it's just a matter of doing the math. 80.1 divided by 1.23 equals 65.12 mils. Questions?
Yes, I got a question.
Oh, what's up?
So for this one, I noticed density, mass over volume, right? So the way I had did it, because I did, D equals M over V, I did the 123 times 1 milliliters over 80.1. I just followed the formula. So
Yeah, so you don't need to solve for density. It's already solved for you. Now you're using density as a conversion factor.
okay,
But we can get you started on it.
All right.
gotcha.
Yep. All right. Any other questions? Okay. All right. Again, going back to lecture 1, sig figs. So I think you have 2 questions about sig figs. It doesn't, yeah, it's not, I gave you 4 examples here just for extra practice, but I think you only have 2 sig fig problems. So if you're really stressed about sig figs, do with that information what you will. All right, so identify the number of sig figs in the following equation. So with sig figs, we have our rule of 0, where leading zeros never count, sandwich zeros always. This is really messy, but always. And then it's the trailing zeros that become tricky, right? They are sometimes, and that is if they are after a decimal and non-zero digit. All right, so we're going to put that to the test here. So 2.001, that has sandwich zeros, which always count. So all of these digits are significant. So 1, 2, 3, 4. It has 4 sig figs. All right. Here, 0.0201, we have 2 leading zeros, which never count, leaving us with an additional sandwich zero here, which always counts. So we have 1, 2, 3. So this one has 3 sig figs. All right. 2010, we have a sandwich zero, which is going to count, but we also have a trailing zero. Now, the trailing zero does come after a non-zero zero digit, but it does not come after a decimal anywhere in the problem or in the number. So that zero is not significant. So it's, I'm getting kind of messy here, but 1, 2, 3, 3 sig figs. And for our last number, we're dealing with a sandwich zero, which always counts. But I want to point out that it's times 10 to the third. We might have talked about this, but I just want to remind you that these are placeholders. Those never count into sig figs. And so this number has 4 sig figs, 1.201. All of those digits are significant. Questions? All right. All right, so write the names for the following compounds. Again, you don't have this many. I think you have like 2 namings, maybe 3. But I thought the more practice, the better, since this is from like week 2. So with naming something, the first thing you need to do is there's 2 naming systems. So you need to figure out if it's ionic or covalent. So ionic is a metal and a nonmetal. Covalent is 2 nonmetals. And when we look at the periodic table, we go all the way back to lecture 1. A nonmetal is to the right of that stair step. It's oxygen, nitrogen, carbon, fluorine, sulfur, where metals are to the left of the stair step, and it's things like magnesium, calcium, I'm sorry, not calcium, potassium, calcium. No, maybe I was right with calcium. Yeah, sorry. Long day. All right, so first we need to figure out if these are ionic or covalent. So nitrogen is a nonmetal. It's to the right of that stair step, and so is oxygen. So this is a covalent compound. Carbon is to the right, and so is oxygen. So both nonmetals. So again, this is a covalent compound. And it's the same for CO2. Those numbers are just in a different ratio. H2O2. So hydrogen is the one exception. It is to the left of the stair step, but hydrogen is always the one weird exception where it's a nonmetal. So this again is covalent. Then we have magnesium, which is to the left. It's a metal. We have chlorine to the right. It's a nonmetal. So this is an ionic compound. And potassium to the left. It's a metal. And chlorine to the right. It's a nonmetal. So again, this is another ionic. All right, so we start with 4 covalent. So let's review the rules for covalent. I'm going to put them over here in blue. I'm going to change the pen color here. All right, so for covalent, we basically name them as they're written, and we say the numbers, the small numbers, as prefixes. And we have our table where 1 is mono, 2 is di, and you would get this table on your reference sheet. 3 is tri, 4 is escaping me at the moment. Oh, tetra, and so on. let's see, do we need, oh, we'll need to know 6 here. So 6 is hexa. All right. So we basically, with covalent, we say the name and we say the little numbers as prefixes, with one exception. If the first letter, I'm sorry, if the first element is mono, we drop the mono on the first element. So we'll see 2 examples of those here. So, I wonder if I can zoom in here. All right, so N2O6. So there's a 2 after nitrogen, so this becomes dinitrogen. And then there's a 6 after oxygen, so it becomes hexa oxide. All right. CO, they both have implied subscripts of 1. So you would think it'd be monocarbon, oxide, but when it's mono on the first element, you drop that. So it's just carbon monoxide. All right. Similarly, we have CO2. So again, mono on the first element, we drop it. So it's just going to be carbon. And then we have di for the second element, so dioxide. All right. And then H2O2, that would be dihydrogen dioxide. All right. So that's our covalent compounds. Now we have a different naming convention for our 2 ionic. All right. So I'm going to erase what was over here about covalent. Maybe we'll go to a different color. We'll go to green. All right, so now with ionic, ionic's nice. You just ignore the little numbers, right? And you just say the first element and then the second element with the ending "ide," which is what we were already doing with our covalent. But we were saying we were giving the little numbers prefixes. So our second element ends in "ide." All right, so our 2 examples here, magnesium, chloride. We don't have to say di or anything like that. And our second example, potassium chloride. All right. Any questions about naming? All right. Final question. So what would be the chemical formula between calcium and iodine? So this would require us to go to the periodic table and figure out the common ion charge. And so that's a trend we learned, I can't remember, I think it was right at the start of module 2. So if you don't mind, I'm going to go real quick refresh you with that trend by going to a periodic table online. All right. So the common ion trend is this column right here. 1 is plus, let's erase that. +1. Then it goes +2, skip a few, +3, plus or -4, -3, -2, -1, and then you have the noble gases, which never form a bond with anything. So we wanted to know what the formula would look like between calcium and iodine. So I'm just going to point these out here on the periodic table for us. So calcium is a +2 and iodine is a -1. All right. So that's where I got that. Now I'm going to go ahead and take that back to the Word document. All right, so calcium is a +2 and iodine's a -1. All right, so with making an ionic compound, you always want it to be neutral. All right, so you can think of it that way, or the easier way for people is to flip the charges. So calcium Ca would be Ca, and then you have that plus charge, and then you also have iodine, which has a -1 charge. And so to flip the charges, iodine would take on a subscript of 1, which when we have a subscript of 1, we don't explicitly write it out. And then, I'm sorry, iodine then would have 2, so it'd be CaI2. That would be the correct formula for calcium and iodide together. Whew, we made it. Any questions?
This is a great review. I
Thank you.
didn't see the end, but it was very helpful. Thank you so much.
Thank you. I appreciate it. Any other questions? So one thing that it said at the very top of this, which I'm going to just point out if you didn't read it, it's not an exhaustive practice exam, meaning it's not all of the topics on the midterm, but the ones that I didn't include, I felt were more like definition, true, false based, and that they were a little easier. So just FYI, if you just like an exhaustive list of every topic you're to see is that modified study guide, but this is also like an important document. It really hits all the more mathy ones.
I do got one question. What was when we just found those? What are those the charges? Is that what you said they were?
Yes.
Okay.
Yep. Down here. Yep.
Can you do those one more time? Like show us the periodic table one more time.
Yeah, absolutely. So let me go back. All right. So here's a periodic table. Maybe we'll go in red so it's a little bit more noticeable. So the trend, so you have to know the common ion trend. It's called the common, let's write this, common ion trend. All right. And so it's the charges that they form. So the first category is +1, then it goes +2, skip a few, +3, ±4. And I know it might be confusing when you say plus or minus, but honestly, don't worry about that category. You'll never have anything from there. -3, -2, -1. Now, why we're actually talking about it, there's a question I didn't include, which asks how many valence electrons are in, and it gives you an element. All right. So again, you need a trend for that one. So I'm going to write that trend here in blue, the valence electron trend. And it's kind of similar, only it goes, and again, this is in blue, so it goes 1. So this whole category would have 1 valence electron, 2, skip a few, 3, 4, 5, 6, 7, and then 8. So that one, the valence electron is basically counting across the rows. Any other questions? All right. Well, I'm going to stop the recording. And I will just hang out here until y'all log off. So I bet there's somebody out there that has a question. They're just holding back till like there's one person left. So thank you all for coming. And I wish you good luck on Wednesday. Reminder, it's going to be in the lab room.
Thank you.
Thank you.